Folks, in this video we're going to look at the principle of superposition and its consequences, and those are going to be key for understanding our solutions to nth order linear differential equations. At the heart of understanding the principle of superposition are linear transformations, and while we don't need all of the tools from linear transformations, we need a little bit of them. So this video is first going to start off with a review of linear transformations. If you haven't seen it before, this will be a good time to take notes. And if you have seen it before, I think that you'll find that this is just a helpful review anyway. So let's suppose we've got two real or complex vector spaces. I'm calling them V and W. Then a linear transformation is a mapping from one vector space to another that has certain characteristics. So going forward, we're going to go ahead and say that we'll represent this mapping this way. And so this is you can think of it like a function if you want, but we call it a transformation because we're moving from one space to another that tells us how to map vectors in vector space V into vector space W. Now we can define many different types of transformations, but some transformations are going to have some special properties, and we'll call those linear transformations. So we're going to say that this mapping L is called a linear transformation if given two vectors in V1 and a scalar, if we can go ahead and say L of V1 plus V2 is equal to L of V1 plus L of V2. And this might look like gibberish to you. Let's talk through it carefully. What this is saying is that the order in which we do the transformations and the vector addition doesn't matter. We can either add together vectors v1, v2, and then do the mapping to them, or we can do the mapping to the two vectors separately. We can take the linear transformation of the first vector and the linear transformation of the second vector, and we add them together, and we get the same thing. So the order doesn't matter in which we do the transformation and the vector addition. Another way to say that is that vector addition is preserved under the linear transformation. The picture that would go with this, and I think a picture is really, really helpful here, the picture that would go with this is that if we have this here is our vector space V, and over here we've got our vector space W, then we could take these two vectors V1 and V2 in that first vector space, and normally when we add them together, let's say they give us this new vector right here, this would be the vector V1 plus V2. That's what we normally get when we add those two vectors together in this vector space. Well, a linear transformation is going to be a way of mapping from one vector space to another, and what we want to see here is that if we were to take L of V1 and L of V2, so what am I saying here? V1, L of V1 would be where the first vector gets mapped to under the transformation, and L of V2 is where the second vector gets mapped to under the transformation. Well, what I could then do is I've got two vectors in this other vector space W. Let me write W more carefully. In this other vector space W. So what I could do is inside of here I could add these two vectors together. Let's see, let's draw it like that. I could add these two vectors together. This would give me L of V1 plus L of V2. And what we're saying when we say that L is a linear transformation is that this new vector that I got by adding together V1 and V2 in the original vector space gets mapped to the same place. So again, what we're saying here is we can either first add together the vectors v1 and v2. That's what I did here. We take v1, we add it to v2, we get this new blue vector in our vector space V, and we'll do the linear transformation to that, and we end up here. Or if this is a linear transformation, what we can do is apply the linear transformation to v1, we'll end up here. We could apply the linear transformation to v2, we'll end up here, and then we'll add together these two vectors in W space to get this new vector here. The other property of a linear transformation is that it preserves scalar multiplication, meaning if I take a scalar in whatever field I'm working with, here I'm assuming R, and I multiply it to vector v1, So if I start with a vector v1, I scalar multiply it by alpha, and then I go ahead and do the linear transformation to that, I get the same thing as if I had first done the linear transformation to vector v1 and then multiplied it by alpha. Okay. So there's a similar picture that you can draw here. Because this diagram's already gotten a little cluttered, I'll scoot over here. So maybe here is v1, oh sorry, here is vector space v, and here we've got vector space w, and we've got some vector v1 in here. Normally, when I scalar multiply v1 by alpha, I would end up with this other vector in my vector space. Okay. Well, a linear transformation is a mapping from one vector space to another. It's a way of taking one type of vector and mapping it to another vector space. Well, what we're saying here, when we're saying that this transformation is linear, is that if I look at where v1 gets mapped to, I would end up with this. And if I then multiplied that answer, that result by alpha in this other vector field, oops, that should have been a finer point, maybe I end up with this vector right here. Here I'd have A of LV1. And for this transformation L to be linear, then it must be true that if I first multiply my vector by alpha and then did the linear transformation to it, I end up in the same place. Again, what we're saying here is I can take vector V, do the transformation to it, then scalar multiply it by alpha, and I'll end up in this spot here. Or I can take vector v, scalar multiply it by alpha, then do the linear transformation to that resultant vector, but I end up in the same place. So the order in which I do scalar multiplication and the linear transformation doesn't matter. So the last thing I want to do in this introductory video is I want to just practice naming things, because I found that students have a hard time with this. Okay? If I say let's say L is a mapping from vector space X to vector space Y. And if I go ahead and perform, I might talk about performing, I don't know, L of the vector X, and that's going to give me this vector Y here. And the other thing I want to talk about is maybe we'll take L of the 0 vector, and that's going to give me the 0 vector here. So one thing I want to keep in mind here, folks, is as we're working with these vectors in different spaces, is just remembering where everything lives. This vector right here lives in this vector space, the domain vector space. And so that means that this vector here, if I perform the linear transformation on that vector, this vector, L of x, is an element of vector space Y. Okay. So the other thing that often we won't do, but I'll do this sometimes for you as you're learning this, but oftentimes math books won't do this, is one consequence of linear transformation is that the 0 vector always gets mapped to the 0 vector under a linear transformation. So one thing you'll have to learn how to read here is I've got two different 0 vectors, even though I'm giving the same symbol for both of them. So here I want to clarify that if this is my vector space X and this is my vector space Y, that when I take, maybe here's the vector X that I was just looking at, and so it would get mapped to the vector L of X, which is the same thing as having some, maybe it's got some other name Y. So that's where that vector gets mapped. But what I want to point out is that the 0 vector in this vector space always gets mapped to the 0 vector in this vector space under the transformation. Okay. So in this case, it's understood that this vector, I'll write that a little more carefully, this vector right here, this 0 vector, lives in vector space W because it was the result of having done the linear transformation to something that I assume is in the domain vector space. So this is understood then to be the 0 vector, I put X and W, I'm sorry folks, this should be Y and this should be X. So this is understood to be the 0 vector in the domain vector space because I'm taking the linear transformation of that vector. And because this vector over here is equal to something that is the result of having done the linear transformation, then I know I must be in this range space over here. So even though I don't usually write 0 with a sub y on that, it's understood that this is the 0 in this vector space here. So what I'd like you to do, folks, is look at a linear transformation, the one that you've worked with a whole bunch. I want you to think about the integral linear transformation. So here, to make you think of it as an integral transformation, I'm writing it I sub f, but it is just your regular integral operation that you've been doing since Calculus 1. So I want you to prove that the integral operator is a linear transformation. So what you need to do is you need to verify that when you take the integral of a sum of two functions, that you can rewrite it this way. And if you take the integral of a scalar multiple times a function, that you can rewrite it this way. And that's just verifying the properties that you know from calculus. But take a look, give it a try on your own, and then take a look at the hyperlinked solution to that. And I'll see you in the next video.